AVL tree from scratch, 74 lines of code in Haskell, simple program. This is a random numbers list, banks, and I have balanced AVL tree. Hello guys, topic of our today's video is inserting into the AVL trees. So actually we will implement the AVL tree data structure with insertion. I assume that you know a little bit theory about AVL trees, what it is and how to insert the elements into the AVL trees. So first thing that I must say that the AVL trees actually binary trees, and to represent them binary search trees, and to represent them they can use such data type. I will take it from pretty-print model, which allows me to print the binary trees in the console in the nice way. I do the implementation of this function. You can see video about it. Okay, we taken this data type and I will put it here to see our data type. But actually I will reuse it from this module, pretty-print. You can find this code and the links in the description. Okay, AVL tree is a binary tree, binary search tree. And there is some extra condition that in every node the height of the left subtree minus height of the right subtree is less or equal than 1. So this is somehow the balance factor of every node. And they must check that this constraints always holds for every node. How we do the insertion into the AVL tree? Actually, the first step we do the insertion into the binary search tree, and then we go from the node which we inserted to the root, and by this path we check the balance property in every node when we possibly can find the imbalanced node. But if we don't find it, we can stay the tree as it is with the inserted element, because we do not damage any balance constraints. But if we find this node in which the balance, the first from the insertion point to the root, in which balance broken, we must do some types of rotations of the tree. Okay, I will talk about this rotations later, but now we need to implement some helper functions from which we can start our implementation. And let's implement the first function which do the insertion into the binary search tree. This is very easy function. I will start with the type signature. It takes some ordered A, and it takes some A, and then it takes some binary tree of type A and produce a new binary tree in which we insert this element A. Okay. Let's start from some simplest case, then the insertion into the empty tree constructed that this constructor, as we can see. So in this way, if the insertion in the empty tree, this means that we're creating some node of type A and two empty left and right subtrees. Okay, otherwise, if the insertion in some tree which constructed by this constructor with node A and left and right subtrees, in this way, actually let's mark this element as E, and now we go to some cases what if our element is greater or equal than element of the root of this tree? Then they can say that they can build a new tree with the node E itself, we don't touch it, and left tree also we don't touch, but the right tree they can create by the recursion. So I can run my insert function again with my element A for right subtree, okay. And otherwise, if my A is less than E, then I can create node with element E as itself, but now I do the insertion into the left subtree, okay. I do this recursively and right subtree stay the same. Okay, this was the first function which we need. The second function, of course, we need height function. In this video, I do not go into do much more focus on the optimization, and I will provide some helper function. We will not be very fast. Okay, and maybe in some other videos I do the optimization of this insertion, but now I just want to do this. So our height function, it takes some binary tree of type A and produce to us the integer which represent actually the length of the tree. Okay, and they can say that if that empty tree, we can say that its height is 0 if we have some node tree created with a node, but if the left subtree is empty and right subtree empty, then in this tree we can say that it height also 0 because this tree have only one node without any children. Okay, but what if we have a height function for some tree which have left and right subtree? Okay, so in this case they can say that our height is equal 1 plus the maximum height of the left and right subtrees. Okay, so we can go to recursion here and be done. This is our height function. Of course, it is not very fast. It takes big O from n time, but we can do implementation in which we can somehow denormalize our data structure by adding the height to the this data type and providing some constraints which check on every insertion and deletion, which will somehow modify this denormalized value of this data type. Okay, but now we will stay with this. Okay, let's go to next function. Now I want to implement function which I will call balance, and this function takes some node of the tree, actually node represented as a tree, and return to us the balance of this tree. So actually the balance is absolute value of the height of the left subtree and the right subtree. Okay, what is the balance of the empty tree? We can say that the balance of the empty tree is 0. What is the balance of the tree which consists of some node left and right and they empty? In this case the balance is also 0 because left and right subtrees have 0 height, and if we subtract 0 from 0, this is a 0. Okay, but what if we have balance for some tree which so we have some node here, and for which have some left tree but right tree is empty. Okay, in this case we can say that the balance of this tree is equal to height of the left tree plus 1. Okay, because we have the height of the left subtree which is not empty, and also we have the h which goes to our root node of this tree. And also symmetric case, then we have some so we have some empty left and not empty right tree. In this case we also can say that this is height of right tree plus 1. And last case, if we have not empty left and right subtrees, in this case we must to take the height of the left subtree, subtract from it height of the right subtree. Okay, we need to take these values, and we need to take the absolute value. Okay, of course we don't need this plus here, and actually we done. So this function we can provide any node of our tree, and this function will tell us the balance of the node. Okay, and then when we can use it to find the disbalanced node. Then we go from the inserted element to our root to the top. Okay. Next thing that I want to implement is function which I call Ipob. What it's do? Okay, this function takes some element A, takes some binary tree of type A, and it's built to me the path from the root to this element A. Okay, I can represent this path by the list of the nodes of the battery. Actually, the node is a type of battery, and we can represent these nodes with a list of nodes. Okay, of course we need to have the ordering here, and let's start from some simple case. What if they have empty tree? This means that there is no path. But what if we have some element A, we have some tree which we can unpattern match with the element in the left and right. Then we can go to some cases here. What if we found our element, what if it's equal to our node element? In this way we can define our function as actually t. Okay, actually it is equal to root. This path have only element from the root node, which actually equal to our A. But what if if they not equal? Of course we go to recursion here, and we know that our tree is balanced, and that's why we can effectively find the element. So if the element is greater than E element, current element, then we can take the current node element and add it to the path of the right subtree. Okay, so we need to go to the right subtree and found the path from the root to the node A, and then add to this path our current element, because we started the search from the whole tree. Okay. And otherwise, if our A is less, then they go to the left. Okay. Exactly the same symmetric case. Okay. And now, having all this function, I think we can write function which find the first disbalanced node from the path of the point of insertion to the root. And then they go to the top. They need to find the first disbalanced. Okay, I will call this function find disbalanced. It takes some order in A, and of course it's take A and B tree of type A. This A we want to find, the path to this A we want to find from the root. And it may be produced to us the binary tree of type A. Maybe we can find the disbalanced node, but if all node is balanced, this means that we can return nothing. Okay. And let's do the implementation. Actually, how can I find this disbalanced node? If I have this Ipob function, I can use it. I can run my, so we provide some A and some T tree here. Now I can run my Ipob function and provide to it the element A and the tree. And this function will return me the path from the root to this element. Now I need to reverse this path. And if I reverse it, I will receive the path from the element to the root. And now I can use the find function for this list, which takes some predicate, which will find the first element which obey to this predicate. Not obey, all this word. The first element which satisfy this predicate, and I need to provide this predicate. So I will provide it as lambda function. It takes some node on input, and it must check the balance. This function we already have. We can check the balance of this tree, and it must be greater than 1. If it's greater than 1, this means that it's imbalanced, and this means that they find the first imbalance from the inserted element to the root. Okay, and they defined it by this function. Okay, now I can start to implement my insertion function. Actually, this is the insert AVL tree function. What it takes? It takes some ordering of type A, some A which we want to insert, some binary tree in which we want to insert, and produce to us a new binary tree in which we already do the insertion. So, and let's do the implementation. Okay, if they insert into empty node, in this case, this is very simple. We can just return a new tree with the node A and empty left and right subtrees. Okay. But what is the insertion into the sum tree? Okay. Let's input match this tree. It has some root element E and left and right subtrees. Okay. Here we need to do the implement the AVL rotation function. Possibly we need to do this rotation, but this is not necessary. Okay, what the steps of our insertion? Okay, at first we need to find we need to, at first we need just do the insertion as the binary search tree does. So with this function we can easily do this. We just put the node into the binary search tree and it doesn't care about break the balance or not. So and I will name this tree, then we put the element as unbalanced tree. So we have this unbalanced tree. When we need to find by f disbalanced the first disbalanced root, okay, node. Then we find this. Here we can see that they have maybe type, but this tell us that the can be in situation in which we didn't find this, and this means that it's okay. This will be it will be returned the nothing. But if we find this actually with node will be in disbalanced node, disbalanced tree will be in the just, wrapped with the just, and this means that they need to penetrate into this just with fmap function. And we need to provide the rotation inside it. So we need to somehow rotate this imbalanced element. But what if this expression evaluate to nothing? This say to us that we can use the alternative here, and as the opposite case provide just tree as it is, okay, and just unbalanced tree as it is if we not find that is balanced. And then this whole expression will always be wrapped with just, and this say to us that we can unwrap it with from just function. Okay, and actually this is the main implementation body of this function, but of course I need to define this rotate function, this unbalanced tree function. And we do this with in the where block. Here I need to provide the rotate function, which takes some disbalance node, and we can here on pattern match this node. It has some disbalanced element, and actually I need to extract this element because it will somehow move in the rotations of the AVL tree, and it have left and right subtrees. And what is rotations? Actually we have 4 types of rotations here, and let's write them as cases. So the first rotation is I need to some predicates here, I will define them later. I need to have left rotation. The first case is left rotation. It must be somehow implemented. The first case is left-right rotations, and we have 2 mirror cases. Then we have right rotation and right-left rotation. Okay, and these all the possible cases for which we need to implement our rotations. So, okay, if I in the left rotation case, when I need to run some rotate function which implement rotate case, and I will name it LL rotate, and I need to provide the disbalanced node to this function. Actually this is the tree which we rotate. Okay, when we do this rotation, okay, we will do this later, now I didn't define it yet, but we can do this. When we do this rotation, we will receive some rotated tree. But this is only the part of the whole tree. And how can we get all the tree? All the tree is we can build it by replacing the disbalanced node, which represent the tree, with the new rotated root node or the new rotated tree. Okay, and we can write the function for this. I will call this function replace, which takes some element which point to the node of the tree which represent the subtree, and we need to, as a second argument, provide the new rotated subtree, and as the last argument they need to provide the unbalanced tree. So what we do here, we have unbalanced tree, we have some disbalanced element which we find, then the insert and go to the root, we find the first disbalance, and we have the subtree which we rotated in these disbalanced elements, and we need to take the whole tree and to change this subtree which represented by this disbalanced element with a new rotated tree. Okay, and this gives to us the new the tree which have all the constraints of AVL tree according to our LL rotation. And now actually I can provide the such logic for any of my last three cases here. So I can here I will replace with left-right rotation. Here I need to replace the right rotation, and here with left rotation. Okay. Now we need to implement actually our left rotate, left right rotate, and two symmetric cases. So you can see this picture. This picture shows to us the what they do in the case of left-to-left imbalance. And actually I will use this as a helper to do the implementation of my LL rotate function, of my first function. Okay, what they need here? How can we define our LL rotate function? Okay, look at this picture. Which part of the tree we need here? We need to extract them and first give the names to this kind of structure. So we go to the left and to the left. We have we run our LL rotate function with our disbalanced node. Here I can unpattern match my disbalanced node. So it has some element as the root. Okay, and we also interested in the left subtree with its childs. You can see it on the picture as T1 and T2 subtrees. Okay, and we can actually extract this information via pattern matching. We can pattern match the left node. It has some left element and it has some disbalance left subtree and disbalance left subtree, and also this node have some right subtree, the root node, which is shown as T3 on the screen. Yes, T3. So actually here we have all information to build a new rotated tree. How can we do this? Of course, with the node constructor we can construct the new tree, but this tree will have, as we can see on the picture, the root node now from A goes to B. Okay, and we have this B here as EL. So I define the new node as EL. When from the left we have T1, which is pattern match here as DLL, and we need to construct the new right branch with the node, root node E and DLR left subtree, T2 on the picture, and DR right subtree, T3 on the picture. So actually we do the rotation. That's all. Okay. Now from here I think we can go to we can now implement the RR rotation because it is mirrored and symmetric. Okay. Okay, you can see the right rotation on the picture, the symmetric variant, and here I will just implement it. You can check this, how it works on the picture. We need to unpattern match the nodes in the same way, I think, like this, but because we have the symmetry here, we need to here the unpattern match in the right part of the tree, and of course the interest in the child of the right part of the tree, and the actually here change to element right, and here the change to, because we go to the right and then to left, and here we go to the right and then to right. Okay. And how we do the rotation? We create the new node, the new element, the new root element is ER, which we get from the right. Okay, and it has some new left child with E element and D left and DRL subtrees, and the right subtree is DRR. Yeah, okay, you can check this rotation with the picture. You can stop the video and see the logic. Okay, now let's go to the more complex rotation, left to right. When we have left to right imbalance, how we rotate in this case? We need to do more unpattern matching here, as you can see. So, and let's do it. So, at first we need to unpattern match our main root with the element E, and we need to better match its left part. So the left part have some node with element left, and disbalance the left tree. Okay, and also we need to better match the right part of this left part. So we go to the left and then to the right, and that's right, we also do and better matching. So I will call this node as element is as element from left to right. Okay, you can see this on the picture, and we have this disbalance from left to right, left subtree, and disbalance left right subtree. Okay, and here we have this right subtree, disbalance right subtree. Okay, and this, I think, all the things we need to better match. This is enough to do the rotation, as you can see on the picture. Okay. Now we constructing the new rotated tree. We start from a node, and which root we have here. Let's look at our picture. As you can see on the picture, the node C goes to the root. Okay, and B go to the B stay as it is, C go to the root, and A is go to the left. Okay, now let's implement this. So left to right, when you node element is get it from left to right, then they go. When they build new subtree from the left, with our element from the left, and left subtree, and left subtree. Okay, and then the build the right tree, which built from our root element, and left right subtree, and right subtree. Okay, I think like this. Yes, according to picture. You can stop the video and see the logic, how we better match, and this is matched with the picture one-to-one, with the rotation which represent on the picture. Yes. And let's implement the last case. It's symmetric. It's exactly the same like the previous one, but with the symmetry. Okay, you can see this picture, and now I will just implement it. Right left rotate. So we better match our root node with the element E, but we don't need to better match the left subtree. As you can see, we only need to better match the right subtree. Okay, as picture say to us. This is right to left and balance. Yes, we don't need to better match the left. We only need to better match the right. Okay, and I will do this in pattern matching here. So we have some element from the right. When I need to go deep and then pattern match the left element, it has the element from right to left and the right left left subtree and right left right subtree, and after this it has the deep R subtree. Okay, the on pattern match they didn't on pattern match, and this is a T4, I think. Yes, T4 subtree, and they mark this like with this name, DRR. And having this, I can build the new tree which constructed the this new element, this new left subtree and new right subtree. You can see the picture which contains the logic of this rotation. And I think, yes, I think we do exactly that they need. So this was the hardest part. We do all four rotations. Now, what we need to do? We need to define our unbalanced tree. What is our unbalanced tree? Okay, this is very simple. We do the unbalanced tree just by inserting A to our initial tree as a simple insertion into the binary search tree. Okay, this function very easily, very simple. What we have to define next? Here we need to define these predicates which define the rotations, and also we need to define our replace function. And let's start with replace function. I think it's simple. How can we implement the replace function? Okay, I will call this function replace, and we need to have some ordering A. We need to provide a node in which we do the replacing of the tree, which define to us some point in our tree with subtree. We need to have a new subtree, and they need to have the initial subtree in which we want to replace this, and after that we will receive a new tree, new replace tree. So let's provide A, let's provide new tree to replace, let's provide initial tree which I pattern match here. And now let's define our final replace tree, and we go to some cases here. What if our element is equal to the replaced element? This say to us that we in the actually define this element, and we just need to return the new tree. So if we find it, we replace it. Okay, but what if our element is greater than the E element of the node. Then we can go to recursion. We need to construct a new tree here, which stay this node the same as it is, but the right tree they need to replace with a new tree, which constructed by this function recursively. Okay, we provide new tree and the right subtree. And symmetric case for when our node is less than element. In this case, we do exactly the same for the left tree, and right tree stay the same. Okay, this is a recursive definition, and I think it will do the replacing. What we need to do next? Okay, we have last undefined these predicates. And actually, how I define the types of rotations. So how we do this? When we find the first disbalanced, so at first we insert the node in our binary search tree. When we go from this node to the root and find the first disbalanced node. When we can go to this disbalanced node and go to the inserted node from top to bottom. And then we go from this disbalanced node to bottom to the inserted node. We need to save our path directions. So we can go at first to left or to right, and then we can also go to the left or to right. And I need to save these only two directions from the disbalanced node to the inserted node. And I can do this with some helper function. Let's implement this function. I will give to it special name. I think this will be find path2 function. What I mean find path2? This means that it's finding only first two nodes of the path from this balanced node to the inserted node. Okay. And what I need to provide for this function? I need to provide my A, the inserted node A, and I also need to provide a node or a disbalanced node, which actually is a tree. And this disbalanced node, as we look at it as a tree, it contains in itself this node A, and this means that I can go from this disbalanced node to the A, because this is a balanced tree. I always know where to go, to left or to right, and I can extract this information. And what I defined here? I defined actually the path with the two elements, the two directions. And to represent the directions, I can create a new type D. And I can define this type, data D, as left or right. And these things say to me from where to go, left or right. And when I will have these two things, I can define the rotation to do left left, left right, right left, or right right. Okay, I think this is very intuitive and simple. So how to implement this helper function? So we providing A, or we providing some tree here, and actually I can use recursion here, some helper function go, to which I need to provide the number of steps which I do. I will do 2 steps, only 2 steps. I need to provide the inserted node and the disbalanced tree node. And let's do the definition of my go function. How can I define go function? Okay, it's take this counter to its element A and on pointer match the node, this balanced node. And here we have some condition. If our A, searchable A, is greater or equal than E, this tells to us that we need to go to the right. Okay, and I will add this right to recursively defined new direction path. So I need to run go again, but I need to decrease the counter. I need to provide the A and right subtree, because they have this condition and they go to the right. And otherwise, the symmetric case, they do exactly the same thing, but we go to the left. Okay, we go to the left subtree, and of course we provide left here because we move to the left. Okay, and of course I need to somehow stop this recursion, and for this I need to provide this case. Then we have 0 counter, not matter the other arguments. I need to return the empty list. And also let's define some case. Then we have, for example, empty tree. In this case we also can't go anymore. Okay, and this thing should define to us this path. Okay, so I will actually get the list of these D's directions. Okay, let's derive the show and DQ for this type. I think I need to print them and compare them. Now we can define our predicates. Okay, let's do this. Go to the there, and how we define left. Of course we need to run our find p function at first. We can define this as fp2. We provide our initial inserted element, and we provide the disbalanced node. So we can now get the first 2 direction from the disbalanced to the inserted node. Okay, actually this value, and now we can compare that it equal to the list of left and left. And now we can define all other cases. What if I have left to right? I have left to right here, and right to right. I have right to right here, and right to left. I have right to left here. And that's all. I think we can try to compile this. Of course I need to for all here add for all A, But actually I didn't do any type signatures here. Maybe I don't need it. Okay, let's run our GHCI and load our file. Okay. We have some errors in the Ipob function. Of course. Balance. So I think I need better match braces here. Like this. And it's compiled. Very surprising, I think, that it will be much more errors, but as you can see, it compiled. Okay. Now let's create a function which takes the list of elements and produce the AVL tree from this list. But one important note which I write here, in this video, in the terms of simplicity, I assume that all the keys must be unique. If we provide a way to support similar elements, in this way we need to do more complex data type for this, which have some two elements, one of them will represent the case and one the identification of the elements. We need this because we want to separate the elements of the same key. But here we assume that all the keys are unique. And please check this thing. And now let's do the function which do the insertion. So I will call this function from list. It takes some list, and because I care about what all the elements is unique, I must to check that the length of the initial list is equal to the length of the list. Then I remove all the duplicate elements from this list. Okay. And let's check this. So my length of the list must be equal to the length of the list. Then I remove all the duplicates element from my initial list. Okay. And in this way I can define this function as folder with insertion and some initial empty tree and with the list. But otherwise I will throw the error what we have duplicate elements. Yes, I think we can define it like this. Let's check its load. Okay, reload, and let's try to run our function. List one. Oh, we can see they have this tree. And now I will use the function from my previous video about pretty tree printing, and I will just print this tree, and they can see this tree like this. So let's add some elements, and you can see that I always get the balanced AVL tree. Okay. So no matter which the elements here, I will always get the correct tree. Okay, here you can see all from the right is greater than all from the left, and for this for every node also the we can see that our balance factor is always hold our constraints. The left tree minus the height of the right tree is less or equal 1 by the absolute value. Okay, no matter what the list is, we will always get the correct results. Okay. This is the AVL tree, and we can use it for searching, and it will be pretty fast, log n time, because the height of the tree is log n. Of course, they have a big field for optimization here. One thing to optimize, it's the height function, because it has now time big O from n, but we can denormalize our type to add some height in the height parameter in the nodes, or balance parameter, which we need to support during insertion. And maybe I will do some video about optimization, but of course after the deletion. Then I need to delete from the AVL tree also, and this is not a very simple task. Okay, that's all for today, I think. Thank you for watching. Push like button, push subscribe button. Please write any comments if you see how can I improve this code. Maybe I do some errors. I don't do any testing. So guys, thank you. See you in the next meditation video. Bye bye.